In Chapter 9, Section 3, we're going to learn how to simplify, add, and subtract expressions that contain radicals. Let's begin with these examples. We're going to simplify these radical expressions. First, we have the square root of 40, and you may recognize that 40 is divisible by 4, which is a perfect square. So let's rewrite this as the square root of 4 times 10. We can now split this into the product of two radicals, the square root of 4 times the square root of 10. And with 2 being the principal square root of 4, this simplifies to 2 root 10. Now I want to show you a second way to look at this same expression. Consider that the prime factorization of 40 is 2 cubed times 5. So we can write the square root of 40 as the square root of 2 cubed times 5. Looking at these four factors, we have one pair of 2's. We have a 2 squared, another 2, and a 5. And separating these, we have the square root of 2 squared times the square root of 2 times 5. The square root of 2 squared is simply 2, and the square root of 2 times 5 is the square root of 10. In the first method, I used my knowledge of perfect squares to divide 40 by a perfect square, 4. In the second method, I simply looked at the prime factorization of 40 and then separated any pairs that I found. Let's do this again with the cube root of 280. In the first method, I'll use the fact that I know that the perfect cube, 8, divides 280. 280 is equal to 8 times 35. So I can rewrite this as the product of the cube root of 8 and the cube root of 35. The cube root of 8 is positive 2, so this becomes 2 times the cube root of 35. Now let's simplify the same expression using the prime factorization of 280. 280 is equal to 2 cubed times 5 times 7. So the cube root of 280 can be written as the cube root of 2 cubed times 5 times 7. Since this time we have a cube root, I want to look for sets of 3 matching factors, and we have one such set, 2 cubed. So I'll separate this into the cube root of 2 cubed times the cube root of 5 times 7. Simplifying, the cube root of 2 cubed is simply 2, and the cube root of 5 times 7 is the cube root of 35. So whether you rely on your knowledge of perfect cubes or use the prime factorization, you get the same result. Let's head over to example 2. In example 2, we are again simplifying radical expressions. This time we have variables involved. We'll start by looking at the fifth root of x to the 33rd. Since we have a fifth root, we can easily simplify factors that are raised to a power of 5. Consider that x to the 33rd is equal to x to the 5th times 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 x to the 3rd. Each time we have the fifth root of x to the 5th, that simplifies to a factor of x. So this becomes x times x times x times x times x times x times the fifth root of x cubed. Or simply x to the 6th times the fifth root of x cubed. Let's look at this in a slightly different way. We have the fifth root of x to the 33rd. Notice that when we rewrote x to the 33rd, we had 6 factors of x to the 5th, or x to the 5th to the 6th, with an x cubed left over. X to the 5th raised to the 6th is the same thing as x to the 6th raised to the 5th. So now we have the fifth root of x to the 6th to the 5th times the fifth root of x cubed. Well, the fifth root of x to the 6th to the 5th is simply x to the 6th. So we have x to the 6th times the fifth root of x cubed. Consider the following relationship. We have a 33 as our power, and 5 is our root. And 5 goes into 33 6 times with 3 left over. Notice how this translates to simplifying our root. We had the fifth root of x to the 33rd, which can be simplified as the fifth root of x to the 5th to the 6th times the fifth root of x to the 3rd. When you take the power and divide it by the root, you can simplify the expression quickly and find perfect fifths, or perfect nth roots. In general, we can write that when we're simplifying the nth root of x to some power p, if p divided by n is equal to some quotient q plus some remainder over n, then this rational expression simplifies to become x to the q times the nth root of x to the r. Let's try this out with our example of the cube root. We have the cube root of 378 a to the 20th, b to the 10th, c to the 6th, d squared. We'll simplify this using the generalization that we just found. Consider that 378 is equal to 27 times 14, with 27 being a perfect cube. Now let's look at a to the 20th. The largest multiple of 3 that is less than 20 is 18. So I'll write this as a to the 18th times a squared. A to the 18th is a perfect cube. Now let's look at b to the 10th. The largest multiple of 3 that's less than or equal to 10 is 9. So I'll write this as b to the 9th times b to the 1st. C to the 6th is already a perfect cube because 6 is a multiple of 3. And looking at d squared, 2 is smaller than 3, so we won't be able to pull out a perfect cube. Let's look at each of our perfect cubes. We have 27, a to the 18th, b to the 9th, and c to the 6th. The cube root of 27 is 3. The cube root of a to the 18th is a to the 18 divided by 3, or a to the 6th. The cube root of b to the 9th is b to the 9 divided by 3, or b cubed. And the cube root of c to the 6th is c raised to the exponent of 6 divided by 3, or c squared. Now let's consider what's still left inside our cube root. We have a 14, an a squared, a b, and a d squared. And that simplifies this radical expression. Two radical expressions are considered like radicals if they have the same index and the same radicand. In other words, we need to have a matching root and the inside of the root needs to match as well. And we can combine like radicals in the same way that we combine like terms. Let's look at example 3. In this first expression, we have 4 terms. 9 root 2 and negative 14 root 2 are like terms because we have like radicals. They are both square roots, so they have the same index, and they are both root 2. They have the same radicand. Similarly, 5 times the 4th root of 3 and negative 2 times the 4th root of 3 are also like terms. They are both 4th roots, and they're both 4th roots of 3. They have the same index of 4 and the same radicand of 3. Simplifying, I have 9 root 2's minus 14 root 2's for a total of negative 5 root 2. We also have 5 times the 4th root of 3 and negative 2 times the 4th root of 3 for a total of positive 3 times the 4th root of 3. Let's take a look at this next expression. 6 root 2 and 10 root 2 are like terms. They have a matching index of 2 and a matching radicand of 2. These are not like radicals, however, with negative 5 root 7 and negative 4 root 7. Just because they are all square roots does not make them like radicals. They have to have the same inside or the same radicand as well. Combining 6 root 2 and 10 root 2, we have a total of 16 root 2. And combining negative 5 root 7 and negative 4 root 7, we have a total of negative 9 root 7. Let's take a look at one more example. First, in example 4, we have the square root of 180 plus the square root of 5. At first glance, it may not seem that we can combine anything or that we have any like radicals. What we need to do first is simplify each of the radical expressions and then look for like radicals. Doing a quick check, you'll discover that 180 is divisible by a perfect square. It can be written as 36 times 5. And with the square root of 36 equaling 6, we can rewrite this as 6 root 5. Now we have 6 root 5 plus another root 5 for a total of 7 root 5. Now let's look at this next expression. At first glance, there's once again not any like radicals, but we need to simplify each one first. Let's start by looking at the square root of 90. 90 is divisible by 9, a perfect square, so we'll rewrite this as the square root of 9 times 10. And with the square root of 9 equaling 3, this becomes 3 root 10. Now let's look at negative 4 root 45. 45 is also divisible by the perfect square 9, so we can rewrite this as the square root of 9 times 5. And since the square root of 9 is 3, this becomes negative 4 times 3 times the square root of 5. Next, we have 3 times the square root of 250. 250 is divisible by 25, a perfect square. So we'll rewrite this as 3 times the square root of 25 times 10. And since the square root of 25 is 5, this becomes 3 times 5 times the square root of 10. Last, we have 8 times the square root of 80. 80 is divisible by 4, a perfect square. It's also divisible by 16, a larger perfect square. So let's rewrite this as the square root of 16 times 5. The square root of 16 is 4, so this becomes 8 times 4 times the square root of 5. Now we do have some like radicals and we can combine like terms. Quickly simplifying each term, we have 3 times the square root of 10 minus 12 times the square root of 5 plus 15 times the square root of 10 plus 32 times the square root of 5. We have a 3 root 10 and a positive 15 root 10 for a total of 18 root 10. We have negative 12 root 5 and positive 32 root 5 for a total of 20 root 5. Now we have simplified this expression by combining like radicals. And that will conclude this lecture video on simplifying, adding, and subtracting radical expressions.